Chapter 4, DPF. Diesel particulate filters, or DPFs, have become standard on highway diesel engines starting in 2007 due to more stringent emissions requirements. The EPA rules required a 90% reduction of engine particulate emissions compared to previous engines. Particulates comprise solid and liquid particles emitted from the exhaust pipe into the atmosphere. You would know these particulates as the black smoke or soot you used to see coming out of truck exhaust pipes. Since the beginning of 2007, soot has become a thing of the past for all new diesel engines. For the engine manufacturers to comply with the new reduction regulation, they were required to add an additional filter in the exhaust pipe after the DOC to capture the particles coming from the engine. Like all filters, DPFs can fill up with the particles. If the filter gets too full of carbon from the engine, the added restriction can cause engine operational problems, sort of like the proverbial potato in the exhaust pipe. To manage this, engine manufacturers have implemented complex processes and equipment to manage the cleanout called regeneration of the particulate filters. How does a DPF work? This illustration shows what is going on at a magnified level. Exhaust gas with particulates flows into the filter channels. For the gas to escape, it has to pass through the walls of the DPF substrate because the plugs are on either end of the channels. The filter, made of a porous ceramic material, allows the gas to pass through but catches the particulates. Every so often, the engine electronic controls manage a regeneration process to remove this carbon and send it into the atmosphere as CO2. Two kinds of regeneration can occur. Passive regeneration is the first kind. Passive regeneration occurs all the time as a normal chemical reaction that happens when there is a catalyst present. Most DPFs are coated with catalyst material similar to that used on the DOC to facilitate this reaction. If two NO2 atoms enter the DPF and come in contact with some carbon in the catalyst material, then a reaction occurs to convert the NO2 atoms to NO. This reaction oxidizes the carbon to CO2. The CO2 and NO then pass through the DPF and out into the atmosphere. This reaction eliminates the carbon accumulated in the filter. The problem is that the engine does not make enough of the NO2 to get rid of all the carbon it puts out. Therefore, another process is necessary to keep the filter clean. Active regeneration is the second kind of regeneration. This process oxidizes the carbon naturally, but works at a higher temperature than passive regeneration does. This graphic illustrates the oxidation process of the carbon and how the exhaust temperature needs to get to 600 degrees Celsius or about 1100 degrees Fahrenheit. Normal diesel exhaust temperatures do not reach these levels often, so the system has to create this temperature by injecting diesel fuel into the exhaust pipe after the turbo and use the DOC to oxidize it. The fuel oxidation will heat the exhaust gas to the levels where all the carbon in the filter oxidizes. Actively injecting fuel is why this is called active regeneration. To manage this fuel injection process, engine manufacturers had to add an extra or seventh injector to the engine along with the fuel lines, coolant lines, and other hardware to assure that the systems will work in this boiling environment. So how is all of this hardware managed? Engine manufacturers use temperature sensors, pressure sensors, and the engine controls to manage the overall system. A DOC/DPF system comes with a canister that contains the DOC and DPF with connections for the exhaust gas to get in and out. Also, the system has at least 3 temperature sensors: a dosing injector, fuel lines, coolant lines, electrical harnesses, and a pressure sensor that senses restriction of the DPF. This restriction needs to assure the filter does not become too plugged with carbon, and also for diagnostic purposes. In our next video, we'll cover the newest addition to the after-treatment systems, selective catalytic reduction, or SCR.